Good morning, everyone. So usually my students complain that I speak way too loud, and it's going to be exacerbated by this microphone, so my apologies. I don't know how to put the volume down. So first of all, thanks to the organizers to the amazing opportunity to speak today. And I'm going to speak about quite a long-term project that started, honestly, in 2007, when I published, Tim Porter and I published a paper and then kept on discussing over Skype time and again, and almost 20 years after the second paper came. And it's about extended TQFT, actually one extended TQFT, categorifying Quinn's finite total homotopy TQFT. Let me just say the legal things. So this was supported by a Liverhome grant, an FCT grant, Portugal. They already finished. And current grant is this EPSRC program grant, Combinatorial Representation Theory, whose subtitle is Discovering the Interfaces of Algebra, Geometry, and Topology. And by the way, we're hiring, so just send me an email if you might be interested. Right, so again, thanks for the opportunity to speak. And let me just start by defining what is a TQFT. And Alexis already spoke a bit about it 2 days ago, but the topic were HQFTs. So TQFTs have a bit less structure. So we start by considering the category. I'm going to call it N cob, and N is a non-negative integer, okay? And the objects are manifolds. Actually, let me say are closed and manifolds. So I always need a smooth structure, otherwise I don't even know if this category is well defined. So here is a geometric representation of a manifold. Let me call it sigma. And I need to explain what morphisms between manifolds are. So if I have a manifold here, sigma, and here another manifold, which I'm going to call, oops, I shouldn't have done this like this. Let me call this thing sigma prime. So one torus and the disjoint union of two tori, and a cobordism. So a map in this category N cob is a cobordism, which I'm going to represent like this. Okay, so essentially I have a manifold M of one dimension up. I have a map I from sigma into the boundary of the manifold M. I have a map I prime from sigma prime into another component of the boundary, and the only condition I'm going to put, I don't want to get into much technicalities, is that if I put I and I prime together, I obtain a parameterization of the boundary. Okay, so let me just write it like this. So I prime, which goes from sigma disjoint union sigma prime to delta M, is a diffeomorphism. I'm not going to have any orientations here. It's not needed. If you want to put cohomology class in Quinn TQFT, then you need orientations. But from now, it's not needed. In fact, for Quinn's TQFT, the smooth structure is not needed, but to construct the category of manifolds and cobordisms, you do need the smooth structure because you, for example, you need coloring of the boundary and lots of technicalities. By the way, this construction is slightly more complicated than some references imply. Okay, let me quickly say how you compose things. Pardon? I'll get there in a bit. So let me say so. Let me say more rigorously, so more precisely. So homomorphisms from sigma into sigma prime are diagrams like this. just write to, I'm going to write it like this, sorry. Okay, so I and J, and indeed we have some equivalence relation. Let me just say the equivalence relation is a homeomorphism from M into M prime, which preserves the inclusions of sigma and sigma prime. It's the obvious diagram. I'm going to draw several similar diagrams later on. Yes? This is a diffeomorphism. You're parameterizing the boundary of M. Yes, I'm talking about smooth manifolds. Yes, you need smoothness. Without the smoothness, you don't have colorings in general, so you don't have identities in this category. There's lots of technicalities involved. I think this construction appeared originally in a paper by Milner, which wanted to explain the proof of the Poincare conjecture by Smell. It's called Notes on the Proof of the H-cobordism theorem, where he actually constructs all of these things. There's actually lots of technicalities, but it's very well written. Milner style. Right, so what's the composition? And I want to maybe draw a few more diagrams. So how do you compose cobordisms? So if you have two cobordisms, so what you do, so you essentially do the obvious push out of M and N. Maybe I should draw another diagram because I ran out of space. I was wanting to continue that diagram there, that drawing, but then I ran out of space. But this is the way you compose things. You do the push out, and the idea is that you glue this cobordism with this cobordism along this manifold. Okay, and some details need checking, but they've been checked all the time. So this is a push out in the category of topological spaces. Then you need to put the smooth structure. The smooth structure is not unique, but since we are considering things up to diffeomorphism, you have a uniquely defined composition. Right, so good. And I believe this is where I should go now. So a TQFT. Yeah, sure. Right. So the identity on sigma is this cobordism. Sigma times I, sigma. And I need to explain how you do the include. Actually, maybe I should say it's sigma times 0, 1. Okay. And the boundary of sigma times 0, 1 is sigma times 0, disjoint union sigma times 1. So if this is I0 and this is I1, so I0 of x is equal to x0, and I0 of I1 of x is equal to x1. It's a cylinder. This is not the usual category of cospan, because in the category of cospan, the identity would be the identity cospan. This is a resolved version, okay? And that's why you need to consider manifolds up to diffeomorphism, and that's actually one of the reasons why I need a smooth structure for things to work. There's actually a lot of devil in the details, but I don't want to get into these details because they did keep me busy, because I do tend to obsess about the details. They do keep me busy for a long time. Okay, let me just quickly say, but let me say this is doable. First construction is in the 1960s. I think John Milner Notes on the Proof of the H-cobordism theorem. So what is a TQFT? So a TQFT is a symmetric monadal functor from, am I using N or D? N. N cob into vect. the category of vector spaces. And so the way to visualize things is, suppose we have a cobordism, which I'm going to write like this, and notice that these things are defined up to diffeomorphism. Actually, there's an equivalence relation. This is the diffeomorphism equivalence relation, so I should probably put here equivalence class of M. But how does this functor look like? So sigma is sent to a vector space. I'm going to call it F of sigma. Okay. So sigma prime is sent to another vector space, which I'm going to call F of sigma prime. And since I have this cobordism, so this manifold of one dimension higher connecting sigma and sigma prime as it is represented upstairs, I now have a map, a linear map, which I'm going to denote like this. Actually, let me just maybe make the notation slightly less onerous to write on the whiteboard, actually blackboard. Okay, so this gives a linear map from vector space F of sigma to vector space F of sigma prime. Okay? And this satisfies, well, natural compatibility conditions. Actually, let me not call natural because you should never use natural when you're speaking about category theory. I have to put obvious. Okay, so among the things, so if you glue one cobordism with another cobordism, the linear maps should compose. So the linear map associated to the gluing of two cobordisms is the composition of the linear maps you get, and then we have some compatibility with the disjoint union, but I don't want to get into these details. And saying this is obvious, some things are actually not so obvious, but they are well written in a lot of places. Catherine.
So people could be wondering, I mean, if you're not assuming that it's oriented, then how do you distinguish a cobordism from sigma to sigma prime and one from sigma prime to sigma?
It's essentially just the position. You say what is the first and what is the second. So it's you divide the boundary into two components. It's the inner boundary and the outer boundary.
You always have a pair of linear maps, one from sigma and
yeah.
to F of sigma prime, and usually one of them is the dual of the other.
Yes.
Here?
So would you have this? Actually, think about it, but it's not.
We can interpret each one.
Yeah, but then goes. I mean, could have another direction. I mean, this is.
Yeah, the ordering of II prime.
Yeah. Yes.
Probably we need to assume the symmetric monotopic is rigid.
Not quite. Not quite. This comes after. Yeah. Right. So, where was I? Yes. Okay. So, let me just do what I promised, which is to explain this. Sorry. Quinn finite total homotopy TQFT. So what is Quinn TQFT? So you need a bit of data, which is B, a homotopy finite space. And each different B will give you a different TQFT, and by the way, this works in all dimensions. And what does it mean to be a homotopy finite space? I'm just going to write a mouthful of things. Okay, so B has a finite number of path components. Each of which with a finite number of non-trivial homotopy groups. Not finished yet, sorry. All of which are finite. Ooh, sorry. So, piece of data that you need, a space B, logical space, probably a CW space, with a finite number of path components, each of which has a finite number of non-trivial homotopy groups, and all of them are finite. So, e.g., if G is a finite group, then BG is homotopy finite. I'm just going to abbreviate with HF. Okay, so the classifying space of a group is in a spherical space, as was mentioned 2 days ago, and the fundamental group of classifying space is G. So if G is finite, you get a space with a finite number of path components, each of which has a finite number of non-trivial homotopy groups, all of which are finite. Oops, I'm tired now. Okay, so there are other examples. For example, G could be the classifying space, so B could be the classifying space of a groupoid, could be the classifying space of a finite two group, could be the classifying space of a finite simple issue group, and there are plenty of examples. Okay. Right. I'm not sure that I erased the right thing. Right, so what can you do with the homotopy finite spaces? You can define something which is called the homotopy content. Which is denoted by chi pi of B. And this is very similar to the other characteristic, except that you look at homotopy groups rather than looking at homology groups. And you do something like this. So sum X in the set of path components of B, and now you do a sort of alternating product. So cardinality of pi 1 of B based in X times cardinality of pi 2 B based in X. Then you have here pi 3 BX, and you put the odd people in the bottom, and you put the even people on the top, and so on. So if the space B is homotopy finite, this infinite product is actually a finite product, and this sum here is actually a finite sum. Okay? Right, so where was I? And yes, this is a truly, just for example, just an example. So if in this example where you grab a finite group, the homotopy content of the classifying space is simply 1 over the cardinality of G. The homotopy content is actually 1 over the cardinality of G. This is actually very simple to compute. And this is quite a miraculous construction. And let me say there's like this miraculous property. I'm going to write it here. So if we have a vibration of spaces. And when I say vibration, I mean Hurewicz vibration. And E and B are homotopy finite, then the homotopy content of the total space, sometimes called homotopy cardinality, I never know which one I'm using, can be calculated by the following sum. This is equal to sum x and in pi 0 of B, and then you do the homotopy content of the fiber at x, so p minus 1 of x, and then you multiply by the homotopy content of the path component of x in B. Okay, and you start seeing this, you see, okay, there's TQFTs that can be defined, okay? The value on a big thing is some of the values on a small thing, on the smaller things. Right, let me explain this notation. This means path component how much time do I have? Yes, it's fine. All fine? And the proof of this fact, this is just by looking at a long exact sequence of the fibrations, and it all follows from telescopical calculations. So we know that the cardinality of the image is equal to cardinality of G. The cardinality of the image is equal to the cardinality of the group you're mapping from over the cardinality of the kernel. You have a product of a lot of things, they will cancel out, and then you pass to path components, and you still need to use a bit of vibration theory, but it's all very classical. It's all the type of things you can find in any book on algebraic topology. Okay, right, so this is a powerhouse for Quinn's TQFT, and let me then quickly explain how it's constructed, because I would like to speak about the extended version, and I have no idea what I should erase. I should have enumerated the pages. Right, and now I probably should become slightly more abstract, and instead of already defining Quinn's TQFT, I want to move to a more homotopy theoretical setting, which will facilitate then introducing the extension. And I'm going to define the following thing, which is a fibrant span. So a homotopy fibrant, a homotopy finite, fibrant span is a diagram as something like this. And by the way, re-answering the question that Katrin said, so there's always like this idea, what is the first and what is the second? But it's a good question. I should clarify this thing. So it's a diagram looking like this, and the conditions are that x, m, and y are homotopy finite. Okay, and that if you pass to the model category of spans of spaces, this is a fibrant object. And what does it mean in practice? This means that if you put P and Q together and look at universally defined map from M into X times Y, this is a fibration. Okay? And I'm going to say again, when I say fibration, I mean Hurewicz fibration. Okay? But it's only going to be visible. So in fact, I'm not even sure this would work for Serre fibrations, because there are so many tricks that I don't even know if it would work. Okay, so this is our main thing to start from, the notion of a fibrant span. And I'm going to now turn the definition of NCOB upside down. And I have a category, which I'm going to call HF span. Okay, so objects are HF spaces. Okay, and morphisms from X to Y are fibrant spans from X to Y, which always give then a fibrant span from Y to X, but think of these things as being directed. Okay? So I'm going to write things like this. So spans, which are fibrant. And by the way, there is an equivalence relation here. I want to consider the two spans to be equivalent if they are fiber homotopy equivalent. Okay, this can all defined. I'm not speaking nonsense. It can be done. Right. So, question to everyone: where should I go? Oh, I think I'll go here because I want that diagram there. So, what's the identity? So, what is the identity of X, a fibrant span? So, I think semi-answering the question from Alexander a few minutes ago, if you're looking at categories of spans, this would be the identity that would usually be considered. Don't write this down because this doesn't work, the identity span, but this is not fibrant. Well, unless X is the empty set or the empty space. So the identity of X turns out to be equal to the space of paths. Sorry, I use these exponential notations for function spaces. Okay, so what do I mean by X power I? This is equal to the space of all gammas from the interval 0, 1, i.e. the interval, into X. And you always give these things the compact open topology. And I need a source, I need a target, and you probably guess that the source of gamma is equal to gamma 0, and the target of gamma is equal to gamma of 1. So theorem, we have a category whose objects are, whoops. We have a category whose objects are homotopy finite spaces. Morphisms are spans, or homotopy fibrant spans. So homotopy finite fibrant spans. Sorry, too many mouthfuls. And the identity is this resolved identity span. Essentially, you're replacing the identity span by a fibration. You could actually do this thing with homotopy, pullbacks, etc. Right, I did not explain what the composition was. I think it's important to explain very quickly what the composition is. And the composition, let me just write it down here. So what's the composition? So the composition of fibrant span with this fibrant span is done dually to what I have done there. But instead of having push-outs, I have pullbacks. So I put here m times n over y, and I have this pullback. But I'm not going to say very basic, because algebraic topology is not basic, but by using very classical homotopy theoretical techniques, this is actually a fibrant span. Okay, so a lot of things to check. For example, that this is homotopy finite, that if I put P and Q together, I have a fibration, but everything works out fine. And it's actually not that hard. It's just about checking things. John.
Coincides with the homotopy pullback.
Pardon?
Coincides with the homotopy pullback?
Yes and yes. So notice that there is this equivalence relation. It coincides with homotopy pullback because I am forcing all of these maps to be fibrations. That was just to avoid using homotopy pullbacks and have a slightly less loose construction.
And in this equivalence relation, you're modding out by honest homotopy equivalence.
Fibered homotopy equivalence. So let me maybe write it here. So we need so two things are equivalent if there exists a fiber map and a reverse fiber map, which makes this homotopy equivalent. And things becomes a lot simpler in the fibrant case. Yes, because you need two maps. It's homotopy equivalence. Homotopy equivalence always have things going both ways. Okay, so you need a fiber map going from M to N, a fiber map phi going from N to M, such that psi circ phi is fiber homotopy equivalent to the identity. It's not any homotopy equivalence. It needs to respect these two projections, and psi circ phi is fiber homotopic to the identity. Yes.
Can I also ask a quick question about the origin of this category? So this smells a bit like it's the homotopy category of something you previously derived matrix spaces, so derived spans.
In a sense, yes. To be a sort of derived span. I'm completely sure there is, and that it's like a derived version of the category of spaces and spans. But I did not look into it because we actually wanted to write down explicit formulae. So fibrations were invented because they're extremely mild and things work very well. So for example, this pullback is just things in M times N, which coincide and they map to Y. Let me actually probably write it down. So M times N over Y, this is a space of pairs of the form Mn, such that P of M is equal to Q of N. It's quite a simple thing.
Yeah, but this would then be implied by forming a homotopy category, because then you would pass to the bifited objects and then you automatically.
Yeah, but you want explicit formula. It's better to stay in the fibration. I mean, it's known when you do homotopy theory, before doing a push out, replace maps by cofibrations. Before doing a pullback, replace maps by fibrations. If you do model category theories, look at derived functors, but I'm going to do this classically. Especially in the later construction, this classical point of view is quite useful. So how much time do I have? Like half an hour? Right, and okay, so I have not categorified anything yet, so where should I go now? I'm going to leave this here. I want these two blackboards. Right, there's more going on here. And I shouldn't, I erased something I shouldn't have erased. But that's okay. Right, so we have a functor. Let me call it F. I like to call a cat meow. Functor F, no imagination, from homotopy fibrant spans into the category of vector spaces. Okay, and what is it that we're going to do? And we send, actually I'm going to write it like this. So we send X to the space of path components, which you linearize. And of course, there's lots of information being lost, but we'll get to it later. So you would also then send y to the free vector space on the path components of y, right? And now I need to think of the map of vector space associated to this span. And what do I do? I'm just going to write down its matrix elements, okay? So let x be something in x, let y be something in y. So I need to say how the path component of x in x connects under this span with the path component of y, just using Dirac notation. Okay, so I just need to say what this matrix element is. So I have a linear map from this vector space to this vector space. So the set of path components is the basis of the first vector space. Set of path components is the basis of the second vector space. So I just need to say what this matrix element is. And what you do, you compute the homotopy cardinality of, now I need to call things by names. You compute the homotopy cardinality of this fiber. Okay? And there's another normalizing factor which I'll speak about in a bit. Okay? Is this clear? Does it all make sense? Remember the homotopy content, which I've already erased. I spoke about it a few minutes ago. Yes? No, this is just matrix element. So it's say that it's a matrix. Okay, this is the enumerate the elements of this. Enumerate these path components. Enumerate these path components. A linear map is a matrix. This is the matrix entry. But it's natural to enumerate it. So I'm going to look at this path. There's sound coming from here.
You are sort of using the fact that there's a natural basis of the...
Yes. I'm using a basis. In fact, this is part of why this will not distinguish smooth structures. It's choosing a basis. Everything is rigid, but gives lots of examples, and that's quite a nice categorification. Right. So there's something I need to put here, which I think it is the homotopy content of the path component of y in y, and there are lots of different normalizations you could choose. And let me say that this is a TQFT. Well, not quite a TQFT because you're not mapping from manifolds and cobordisms, but it's a TQFT like object. And let me just say what the powerhouse was. Remember, I mentioned that if we have a fibration, then the homotopy content of the total space was sum over all path components of the basis, of the base space, and then something like chi pi of the fiber times chi pi of the path component. And essentially, that's what makes these things functorial. Okay? So this is, before I answer the questions, this is implicit in Quinn's original paper. So I take no credit for this. And there's a more recent paper by Galvez Carrillo and de Tongs and Koch, in which they do a generalization for this, but more in the context of infinity and categories. Catherine and...
So there's no notion of tensor product that plays a role here. So here you just have a functor.
Product. This is actually symmetric monoidal, but the natural way to, the natural monoidal structure here is the product, because this is dual. This is actually, this X is actually the space of functions, and space of functions on a disjoint union is the product of the space of functions.
So it is symmetric monoidal.
It's symmetric monoidal, yes, but let's leave it for later. Yes, it has all properties you would expect. Someone raise their arm here? Yes. Yes, it's yes, okay, symmetric monoidal. Good, and right, so I have not explained what Quinn's TQFT is. I'm going to finish explaining it here, and then go to what I wanted to do the most today, which was the extension, but I think this was motivation enough. So, so what is Quinn's TQFT? Let me call it FB. So B, a homotopy finite space. So we have a functor from n cob. Let me call this thing, well, I called it FB, we called it FB in the paper, but now I cannot use it. But you have a functor from n cob into HF span. So let me call it by something like maybe this. Okay, and what does it do? It sends X, which is a manifold, to the space of functions on X with values in B. So this, I'll use another notation. Let me write it like this: top X B. Okay? Space of function in X with values in B. So the space of fields you consider is the space of functions of X with values in your homotopy finite space. And right, and what do you do anytime you have a span? Actually, let me not put X, let me put sigma. So anytime you have a span, yeah, this is actually a span. Right, so here I would put top sigma prime B, and in the middle I put top MB. Okay, and the map that goes, so if I have a function defined, maybe I can just put one more thing to make the diagram even more confusing. So anytime I have a function in M with values in B, it restricts to a function in sigma and in sigma prime. So these things actually go the other way around. Okay? And this is the way the functor is constructed. Okay? Restrict the function in the big space to the two spaces. And, well, composition is preserved by abstract nonsense. Because top is a monoidal model category, this sends push out to pullbacks if I pass to function spaces. Okay? And intuitively, a function defined intuitively, I'm sure someone will break this at some point, as I nearly did. So intuitively, this works well because a function defined in the push out is a function defined here, which I have the right restriction to sigma prime intuitively. But I need to work a bit better that the topologies work, but that's fine. So, and what's Quinn TQFT? Now I just put that functor, which I unfortunately called f, and you are in fact. So that's Quinn's TQFT. This is all in his paper, though it was a tiny bit cryptic. Let me say that. Okay, and now I should maybe speak about this extension. Yes?
So generally, how sensitive is Quinn's TQFT? Like, is it a very good one that can distinguish many?
So it does not distinguish smooth structures because homotopy spaces are, well, homeomorphism invariants, but it includes digraph Witten. You need to, this can all be tweaked by putting cohomology class as long as you pass the oriented case. So it includes digraph Witten, it includes Yetter homotopy type TQFT, and well, the sky is the limit. So B can be any space. It could be a 3 type, for example, and that give a whole new type of TQFT. So my main aim when I started doing this was to have actually lots of examples. I got a bit frustrated with some of the constructions of TQFTs. And let me also say, before I continue, all of these things are computable because, okay, this appears to be like a very intractable thing, but you just pass to some combinatorial model for homotopy, and you can very easily compute homotopy groups of function spaces. So if you're just interested, for example, in 2 types, you just work with cross modules and do all of these calculations in the category of cross modules, and then you get exactly Yetter TQFT. You can work with cross complexes. You don't have all of Quinn's TQFT because cross complexes do not model homotopy types, but they still model quite a few ones. And if you're brave enough to work with simplicial groups, then you can do everything. So every homotopy finite space is the classifying space of a finite simplicial group. And, well, all of these spaces become complexes, which are finite. This can all be computed in principle. I don't know how hard it would be. You did do very complete formula for the case B is a 2 type, B is a classifying space of a cross complex. I presume classifying spaces of 2 cross modules would also not be too bad, but it's doable. But this is a general technology. But I would really like to go to the extension because that's what. No question is stupid.
So the Q in QFT means somehow, when I want, I can put an H bar in here. So the first step is clearly classically fast function algebra. So is that second step is from HF span to back? Is there something which we can think about summing over different things in the path and doing some H bars?
Quite possibly. Quite possibly. Yes. So if you could start with a group and compute it by passing to, maybe speak later, but maybe you need to start it with quantum groups. But this, for the moment, this is classical. I don't know how this could be quantized. Other that previously people have done similar things. Anyway, in the last, I don't know how many minutes, maybe 10? Maybe I'll try to be fast. Maybe 10 minutes, I will try to explain how to categorify this and just give a few examples. Maybe I'll look here. Right, so what's this thing of an extended TQFT? Maybe I should start by drawing a diagram, which I usually practice before drawing it on a whiteboard. Actually, in this case, blackboard. And I'm sure I'm going to mess it up, because I always do. Right, so it wasn't too bad this time. Did I do an impossible object? No. Good. Right, so I'm going to look now at extended TQFTs, and if you look here, you have a drawing of a surface, which I hope everyone can visualize. And I have lots of components I'd like to have here, okay? So let me call this here sigma. Sigma will be this point, and also here. Okay. And on this side, I have sigma prime. And by the way, in this case, sigma and sigma prime are diffeomorphic, but they do not need to be diffeomorphic. Okay. On the top, I have a cobordism connecting sigma to sigma prime. Maybe I should call it M. And I have another cobordism downstairs. Okay, let me start drawing things in a more categorical way. So I have sigma, and I have sigma prime. And I need to pay attention to what I consider to be the inner boundary and outer boundary, as I was warned earlier today, but I'm going to write it like this. So I have a cobordism connecting sigma into sigma prime, and I have another cobordism N connecting sigma to sigma prime, okay? And then I have a cobordism of one dimension F connecting bottom to top. I'm going to call it W, okay? Write like this and hint at the categorical notation. Millions of details need to be checked, but if you look at it, you can roughly see these things compose horizontally and vertically, and after checking details for months, years, and never be satisfied with them, this defines a bicategory. Okay? So bicat N cob. I put a hat just to distinguish from the previous things. Right, so what is an extended TQFT? And then an example. So an extended TQFT, actually let me put it like this, a once extended TQFT is a symmetric monoidal bifunctor from this N cob hat. Hat means categorified. Well, some algebraic bicategory. Going to leave it open. So previously we had the category of vector spaces. What to put on the right-hand side, I think, depends a lot on the example you want to look at. And what should I put there today? How much time do I have? I don't have much time. So maybe let me put here profunctors. Or just a particular case of profunctors. So let me call, there's this bicategory. Let me call it VProf, because this is actually not the full category of profunctors. Okay. And what are the objects? So objects are groupoids. Let me call them G. Okay, and morphisms, or one morphisms from G to G prime. Actually, let me just put it H. Okay, are profunctors. Let me write them down as F from G to H. Let me just put this bar. Okay, it's just a notation which is useful. But what are profunctors? Let me say F is a functor from G up times H into vect. Okay, maybe I should unpack this a tiny bit. Let's see what this gives. So where should I do it? I'll do it here. So what do I do? So unpacking. So if X is an object of G and Y is an object of H, we have vector space. Let me call it fxy. Okay. And there's something else I have, which is the fact that the functoriality, which I want to write down because understanding the diagram, it's very easy to understand how the extension ought to exist, because that's something I can dream to explain today properly. And also, so given a morphism gamma in G, and actually let me just put this thing the other way around. Given a morphism gamma from x prime to x in G and a morphism phi from y to y prime in H, I have a machine. So I have linear map. So how should I write this down? We have a linear map from X, from the vector space fxy to vector space fx prime y prime. Okay, and the notation I'm going to use is this notation. It sends an element vxy. Okay, to something I'm going to denote like this. So this means gamma acting on the left on vxy and acting on the right by phi. Is this okay, this notation? So this is a way to pass from vector space fxy to vector space fx prime y prime. Okay, this is probably the best notation to use, and the composition of profunctors is like doing the tensor product of modules over non-commutative rings. You need to apply some equivalence relation. I can explain this later. Just believe me that you can build a bicategory such that these things are the objects, and it's quite a natural thing to construct. I never use natural for category theory because it means something.
Now I missed why it's a bicategory.
So the one morphisms are profunctors, which yeah, two morphisms are natural transformations, but I'm not even going to get there. Thanks for the question. I'm rushing a bit. Right. So perhaps I will very quickly now explain this categorified version of Quinn. And maybe explain a bit of the homotopy theoretical construction. So what is this E Quinn? So let's go back to this fiber and sponge. And what I would like to do is to associate a profunctor to this fibrant span. Okay? And what do? Right, so perhaps let me say this is X. Let me say this is Y. Okay, right, so you send X to the fundamental groupoid of X. And later on, I'll need to actually consider some pointing of these spaces, but I'm not going to do it today. And Y is also sent to pi1 of Y. Y? Right, and now I need to build a profunctor. Okay, so suppose I have an X here and a Y here. A natural thing to do is to look at the fiber as we looked before. So let me say that this is the fiber at X and Y. Okay, so if I have a profunctor, each pair of points must return a vector space, and a very simple way to do it is to do set of path components. Information is being lost here, but it's still quite interesting. And then, whoops, linearize. Yeah, C. Right, so I have vector spaces. And now let's think how to build the actions, because I also need an action of pi1 and pi2, which is sort of compatible on the left and on the right. And again, by using fibration theory, so actually let me call this X prime. No, yeah, it should be X. So now, if I have, let me just put some holes here, okay, because this can have a non-trivial topology. So this is a special function. So anytime, I have a gamma here and a gamma prime here. And let this thing be Y prime and this thing be X prime. The fact that I have a fibration, and this is actually like the parallel transport, but like the homotopy theoretical parallel transport, but there's no connection. That's why I have this pi 0, but if like pick a connection, do the parallel transport, and where things go to doesn't really depend on the connection. Right. And this would be the action by gamma and by gamma prime. Let's just kind of write it like this. So theorem, this is the first step for an extended TQFT. And things work quite nicely and quite non-trivial. And the proof is just brave through lots of fibrations, lots of homotopy finite spaces, and some nasty categorical diagrams. I should probably stop here. Just believe me, this is computable because just pass, for example, to the simplicial theory. You can completely compute homotopy groups of function spaces. If you pass to cross modules or cross complexes, then things become astronomically simpler. So for example, it's known that there is a TQFT sending, there's an extended TQFT sending S1 to the quantum double of the group. That's exactly what you'd get if you do the classifying space of the group BG as your space B. But lots of other things. I should stop now. Sorry I went over time. 5 minutes. You're welcome. Thank you. Yes. Right, so let me say a particular case. Suppose that B, so by the way, now to build Quinn's TQFT, you need to consider those diagrams there, then map to a homotopy finite space, pass from co-spans to millions of things. Well, so not millions, but a few things. But this is the way things work. The details are tricky, but the path is what it is. It's the only thing it could be. But let's suppose that B is equal to BG, a finite group, okay? So a finite group gives rise to a groupoid. And the groupoid is G over G. Actually, it's a conjugation groupoid. So, so the morphisms are things like this. Okay? It's the conjugation groupoid of G. So if you do the groupoid algebra, so the groupoid algebra of G over G is the quantum double of G. So a very nice observation by Siegel. By the way, I did things over profunctors. If you linearize a profunctor, you get bimodule, essentially. So you can work with whatever category you prefer. I think profunctors are better. Bimodules, they destroy a lot of things. So let me say, under this construction, S1 would be sent to the fundamental groupoid of the space of maps from S1 into the classifying space of G. And this groupoid is equivalent to G over G, the conjugation groupoid. And that's why the TQFT you get from the quantum double of a group is a particular case of all of this. I did not explain how to reduce from this infinite thing, infinite groupoid, to this discrete groupoid. That's another step I did not explain, but that's the way to do it. I can explain it a bit better. Okay, this is not isomorphic. It's equivalent. Okay, this one has an infinite set of objects, actually, and countable objects. This one has one object for each element of G. You need to reduce the size of things, but the size can be reduced in a coherent way. I never thought about it. Yes, Morita equivalence. So essentially the algebras you associate to manifold are Morita equivalent, but it's not that they are Morita equivalent. You have a very canonical Morita equivalent connecting them. But to algebra being Morita equivalent means nothing. It's chosen Morita equivalence, which is actually natural and has all sorts of functorial properties. It's written. I think this bit is actually written. Yes? I think this should be fully extended. I mean, if you look at the formula, you could see, okay, this is just the first stage, but it's tricky because tell me a good definition of a symmetric monoidal tricategory. It just doesn't exist. And even what is the pardon? Yeah, but yes. So you could see how it ought to go. But the point is, what is for your domain tricategory, manifolds, coordinates, extended coordinates, etc. I mean, it seems intuitive, but the details are nasty. And then you think, okay, where am I going to map to? I mean, there are all sorts of papers that claim, okay, there's these tricategories of bimodule categories and bimodal profunctors, etc. And I need to actually look at the details and see if the construction is solid enough. I do like to be honest and really check the details of things. It's the good thing about having a permanent position is that I can actually worry about details and not worry about losing my job. Yes?
Maybe I didn't see that correctly, but so the construction in the extended set goes again through this homotopy finite spans, kind of.
Yes, it goes to homotopy finite double spans.
Okay, so then this becomes a bicategory.
No, it does not become a bicategory. but it's almost as good as I can explain it to you. In fact, we thought at first that it was a bicategory, but it's not. So the type of things you have are, sorry. You just write it like this. So right, so this is the type of objects we have. I'm sure I have some arrow going on the wrong direction, but you forgive me. So this thing composed horizontally, composed vertically. First issue, if you do the naive mapping space, it's not certain to be homotopy finite. I don't know the answer. Actually, no, I think it's not to be homotopy finite, but something of the vibrancy whole, because you have these things, and then there's a condition that, okay, this is actually a really vibrant thing. So essentially, you have the conditions that this map to the co-limit, actually the limb over the boundary is a vibration. Okay? Yes, but the uniters fell. You don't have uniters. You don't have natural uniters. You need to actually, so it's a bicategory as long as we stay the image of the mapping space duality. Outside it, I don't know if that's the case or not. Yeah. Okay. Everything composes well. You have uniters as long as you stay in the image of the dualization map. Yeah, it passes through here because this is where this was a sandpit, but this is not a bicategory. It's not a symmetric monodal bicategory, but it's almost as it was in the sense that we can have all formula, but we checked all formulae outside it. Yes, this was a freaking nightmare. Let's say, but the symmetric monodal structure was another headache. Yes.
Are there further questions or comments? If not, then let's thank the speaker again.
Thank you. By the way, this is all on the archive. If you want to have a look. Apologies for the size. It's 200.